So here's the type of problem that I gave in the problem set about determining the quantum number for one of the highest energy electrons in a particular atom. So in this case, we're looking at nitrogen. We notice that nitrogen has an electron configuration of 1s2, 2s2, 2p3. All right. We want to determine the highest energy, where the highest energy electrons are. And the highest energy electrons are going to be in the second principal energy level. So we know we're looking at either the 2s2 or 2p3 electron, but we should know that the p electrons are higher energy than the s. So we have three potential electrons to choose from to answer this question. I'm going to write out the quantum number for all three of them. If you have been asked for one, then just give me one. So another way to look at this is on the energy diagram, and we've shown this as well. On the energy diagram, we have 1s, 2s, and 2p. And we have electrons here, and we have 1, 2, 3. Remember, we cannot pair them until all of our slots are full. All right, so quantum number-wise, we know our n is equal to 1. Sorry, 2, excuse me. Our n is equal to 2 because we are looking at the second principal energy level. We know that our L is equal to 1. Let me make this look like a 2. We know that our L is 1 because we are talking about p orbitals. Therefore, we know our M sub L can be equal to a -1, a 0, and a +1. And if we look at our energy diagram, we realize that we must put 1 in each of the slots. So our M sub S is always going to be equal to +1/2. So we have three quantum numbers for these electrons. And if we were to label the electrons A, B, and C, then I can write the quantum numbers for A, B, and C. And those quantum numbers would be 2, 1, -1, +1/2, 2, 1, 0, +1/2, 2, 1, +1, +1/2. So those would be three separate quantum numbers. All of these are valid for the highest energy, one of the highest energy electrons in nitrogen. And notice this is A, B, and C, so you can correspond these with the electrons that they go to. All right, let's look at the other style of question that I asked. And the other style of question that I asked was determine which of these are valid. So I'm going to write a couple of these. I'm going to write 4 sets of quantum numbers and determine if they're valid or not. Okay, so here we have 4 sets of quantum numbers. And we're going to determine if it is a valid quantum number or not. Okay, let's look at number 1. We have a principal energy level of 3. That means we're in the third period. We have a angular quantum number of 1. That means we're looking at p electrons. We have a momentum quantum number of 0. That means this does fit within the range from 1 to 0, and we have a positive 1/2. Number 1 is valid. That is a valid quantum number. Which electron does it correspond to? Well, if we were looking at the 3p, and we know in the 3p we have 3 slots, we are looking at the middle electron here. This is what we're looking at. All right. Let's look at number 2. We're looking at the second principal energy level, which is second period, but we look at our angular quantum number and we see that it is a 2, and that corresponds with a d orbital. There are no d orbitals in the second period. Therefore, this is invalid. Does not matter. Once you see 2 and 2, cannot be. Let's look at 3. The first principal energy level, we have 0 for s orbital. We have the momentum quantum number, 0 as well, which it should be for s orbitals. We have a plus 1/2. So this is valid. And this will be the electron in the 1s, the first electron. Number 4, we have a 3. So we're talking about the third period. We have 0, so we're talking about the s orbital. We have a 1. We cannot have a 1 based on the rules for the momentum quantum number. It has to be 0 since our angular quantum number is 0. Therefore, this is invalid as well.